We're skipping the fluff and jumping right into a high-stakes scenario that literally costs thousands of Cambridge physics students their top grade every single year. Picture this. You're sitting in your 9702 exam, the clock is ticking down, and you're staring at a heavy mark question about crystal structures and material failure. The way you answer this specific question, it's often the exact moment a grade boundary just slips away. So today, we're taking a teacher-style microlesson approach in this explainer to completely conquer polycrystals and grain boundaries, and we're going to target the mark scheme directly.
So, let's kick things off with a challenge. When a solid material, let's say an aerospace turbine blade, physically fails or breaks under stress, what microscopic feature is the examiner actually testing your knowledge on? Is it A, the solid breaks because the atoms themselves are weak? B, grain boundaries are causing structural vulnerabilities? Or C, there are empty spaces stopping the forces? Lock in your answer right now in your head, A, B, or C. Got it? Make a mental note of it, because missing this core concept is exactly where standard revision falls apart and ordinary answers lose absolutely critical points.
If you chose A, you are definitely not alone, but you've just fallen into the ultimate trap. This right here is the painful learner mistake almost everyone writes. The solid breaks because the atoms themselves are weak. Now, students write this thinking it sounds perfectly logical, but it loses marks instantly because it completely ignores the structural reality of solid-state physics. The strength of a material isn't about individual weak atoms. It's entirely about what happens internally at the atomic or carrier level regarding their arrangement.
What's really fascinating about that mistake is that it reveals a silent expectation examiners have when grading your crystal structure answers. Think of it as the examiner whisper. They aren't looking for a scattered collection of memorized facts, or just randomly dropping keywords. They are looking for a disciplined paragraph connecting a microscopic cause to an observable effect. They want to see that you truly understand how the internal physics dictates the external behavior of the material. If you simply state a correct term without explaining what is physically happening, you are leaving serious marks on the table.
So how do we actually fix this? To get those top band marks with minimal effort, we've got to stop memorizing random labels and start understanding the internal physics step by step. We need to upgrade your revision plan right now from passive reading to active, structured answering. Because honestly, the biggest mark impact comes from making the smallest change in how you format your thoughts. You don't need to write more words, you just need to write exactly what the mark scheme demands.
Okay, let's dive into an authoritative 4-step framework that gives you a completely foolproof pathway to a perfect answer. Think of this as your high-mark exam strategy. Step 1. Definition. Just state clearly what the physical structure is. Step 2. Microscopic mechanism. Describe exactly what is happening down at the atomic or carrier level. Step 3. Observable consequence. What can we actually measure or see happening to the material as a result? And Step 4. Real-world application. Connect that consequence to a specific material or device. Let's walk through this exact sequence using our core topic.
Moving right to Step 1, let's lock down our definition. A polycrystal isn't just one giant, perfectly uniform structure. It's a patchwork of tiny, uniquely angled crystal grains known as crystallites. Imagine dropping a handful of identical square floor tiles onto the ground, but they all land facing slightly different directions, right? They're all tiles, but their orientations are totally random. That is exactly what is happening inside most everyday metals and ceramics. They are polycrystalline.
And that tile analogy brilliantly illustrates our next crucial definition, grain boundaries. Where these mismatched puzzle pieces, these differently oriented crystal grains, crash into each other, you get grain boundaries. These interfaces are the actual defect zones dictating how the material behaves. They're basically regions of atomic mismatch. The atoms here just don't line up perfectly with their neighbors. And this structural disruption is the microscopic root of the material's macroscopic properties.
Now, I want you to pay super close attention to this. In a moment, I'll show you the exact examiner clue that changes your structural analysis completely and practically guarantees those top band marks. You really cannot afford to miss this upcoming clue. But first, we need the microscopic framework that makes that clue incredibly obvious. We have our definitions down, now we have to bridge the gap to those observable consequences. We need to look at what physically happens at the atomic level inside these mismatched boundaries when forces or fields are applied.
So this perfectly illustrates the transition from Step 2 to Step 3 in our framework, microscopic mechanism versus observable consequence. The mechanism is the atomic mismatch at the grain boundary. Because the atoms are out of perfect alignment, they throw a wrench into the normal flow of things. The consequence? Well, this mismatch directly disrupts energy transfer, charge carrier transport, and field response.
If you're talking about mechanics, these boundaries can actually stop microscopic fractures from spreading, which strengthens the material. But if you're talking about electricity, these same boundaries scatter charge carriers, increasing electrical resistance. You absolutely must link the atomic mismatch to the specific disruption.
Let's move to step 4 and see how this builds into real-world applications. Examiners absolutely love it when you link that microscopic mechanism to real materials, because crystal arrangement literally controls defect tolerance in major industries. For example, in aerospace, turbine blades are often engineered to be single crystals to completely eliminate grain boundaries, preventing structural failure under extreme heat and stress. On the flip side, in electronics, the grain boundaries in semiconductor wafers scatter electrons, which is exactly why high-end chips require nearly perfect single-crystal silicon. Structural alloys, however, rely on grain boundaries to halt microscopic cracks. Tying your physics to these real-world uses justifies your scientific reasoning flawlessly.
Okay, let's test this out with a quick spot the error challenge. Listen to this sentence. Grain boundaries are empty spaces in a semiconductor that stop electricity. I want you to pause for a second and predict why this specific sentence, which honestly might sound kind of scientific to an untrained ear, will actually score absolute 0 marks in your 9702 exam. Think about our framework. Think about the definitions we literally just covered. What is fundamentally wrong with the cause and effect here?
Here is the breakdown, and the crucial point is seeing the massive difference between these two approaches. The flawed answer says empty spaces stop electricity. It uses incorrect terminology and a completely vague mechanism. Grain boundaries are not empty spaces, they are regions of mismatched orientation. Now look at the top band perfect answer. Mismatched crystal orientations at grain boundaries scatter charge carriers, reducing conductivity. See how it states the structural mechanism, mismatched orientations. It states the action, scattering charge carriers. And it states the observable consequence, reducing conductivity. This is disciplined cause and effect reasoning instead of vague, scattered facts. This is exactly what the mark scheme demands.
All right, to really lock this in, here is your final minute upgrade checklist. Use these 4 memory triggers for literally any crystal structure question, and you'll be in complete control. Number 1. What is it? Define the polycrystal or grain boundary. Number 2. What changes inside? Describe the microscopic atomic mismatch. Number 3. What is observed outside? Explain the consequence on transport or strength. And number 4. Where does it matter? Link it to a turbine blade or a semiconductor. If you can answer these 4 prompts aloud from memory, your revision for this micro topic is totally secure and exam ready.
So we've thoroughly mastered the theory and the answering framework for written questions. But there is a massive, unresolved problem remaining. The Cambridge examiners love to take this exact theoretical concept of grain boundaries and bury it deep inside complex data analysis traps in the practical evaluation papers. If you only know the theory, but you don't know how to apply it to the data analysis traps in those practicals, you are still going to drop critical top-grade points. Recognizing the flaw in a materials data table requires a completely different skill set.
Because as the saying goes, understanding the theory is really only half the battle. The true test is applying it when examiners try to hide these concepts inside complex data analysis traps. So as we wrap up this explainer, I want to leave you with this question. If you were handed a flawed data table right now regarding the tensile strength of an aerospace alloy, would you know how to spot the microscopic grain boundary defects hiding in those macroscopic numbers? The foundation is set. Now it's time to test your eye for the data.